It's my great pleasure to introduce Muyinatu Bell, who is an assistant professor of electrical and computer engineering, as well as biomedical engineering and computer science from Johns Hopkins University. She has several great papers that I've read a lot of them. And today she's going to be telling us about ultrasound image formation in the deep learning age. So Muyinatu, the floor is yours.
Thank you so much for the nice introduction. Hello, everyone. My name is Muyinatu Bell, and it is my pleasure to be here, to be invited to talk to you about ultrasound image formation in the deep learning age. So many of us are familiar with ultrasound. It is ubiquitous in the clinic, and this is a standard clinical setup showing a sonographer holding an ultrasound probe and viewing an ultrasound image on the screen. Now, the first medical ultrasound image was created in the 1950s, and in the 60-year history of ultrasound up until now, all images that sonographers see on the screen start as raw data sensed by the ultrasound probe. From this raw data, we traditionally create the images that sonographers see on the screen after passing through the beamforming process. This beamformed image can then be used to segment structures of interest. While deep learning has traditionally been applied to the beamformed image to segment structures of interest, by the end of this talk, I hope to give you a greater appreciation of the novelty introduced by my lab, which breaks from traditional applications of deep learning to beamformed images and starts with raw data to replace the mathematical component of image formation with deep learning to produce a range of more desirable images. One reason we are pushing this frontier is because we understand the breadth of anatomical structures that can be imaged with ultrasound, as shown here, and because of the many benefits of ultrasound imaging, such as it being safe and portable, it being able to provide real-time images, allowing us to see this beating heart right before our very eyes. It is cost-effective, and it can provide information for both diagnoses and for surgical guidance. Despite these benefits, ultrasound images suffer from several outstanding challenges that have persisted in its 60-year history. For example, ultrasound images are known to be noisy. They're known to contain a granular texture appearance known as speckle. They have acoustic clutter, which causes regions that should appear black to appear as if there's signal within them. They suffer from sound attenuation at depth, as well as poor resolution at depth. And ultimately, these challenges make ultrasound images difficult to segment and difficult to interpret. At the heart of these challenges is the basic idea that ultrasound images are thought to have poor quality. Several techniques have been implemented to overcome this list of challenges, such as spatial compounding, which addresses speckle by smoothing out tissue texture. Doppler imaging, which enhances blood flow and could be an interesting approach to vessel segmentation. Harmonic imaging, which allows us to reduce acoustic clutter, although it doesn't work well in some cases, particularly for patients who are overweight or obese. And then we have this method that I developed and created during my PhD dissertation, which is coherence-based beamforming, and it effectively reduces clutter in cases where harmonic imaging fails. However, it is computationally intensive and has yet to be implemented commercially as a result. We also have elasticity imaging, which allows us to image the stiffness of tumors and could also be an interesting approach to tumor segmentation. And there are other techniques that also exist to provide similar benefits to those summarized here. However, none of the benefits and advances summarized on this slide simultaneously address the long list of outstanding challenges that have persisted in the 60-year history of ultrasound imaging. Yet they all rely on the same raw ultrasound data to make images. So I believe that this requires us to rethink the image formation process to determine if we can address multiple challenges in a single step. And this is what motivates me to explore deep learning as a potential solution to address multiple challenges in a single step, starting with the same raw data. I would like to see us transform noisy, poor contrast images created through the mathematical models that inform the traditional beamforming process into a desired image that only displays structures of interest after taking the alternative route of applying deep learning methods to the raw data. Then I'd like to add to the information provided by the ultrasound image, augmented with another imaging modality that also relies on the same ultrasound transducer to show us very clearly where a difficult to find structure that is sensed by that alternative imaging method, such as finding this difficult needle tip. This is the concept of the topic of my Trailblazer Award from the NIH. At the time that I proposed this idea, I was not aware of anyone thinking in this direction. So I am excited to tell you about the novel and innovative work that we conducted in my lab to literally blaze a trail for the merger of beamforming, ultrasound image formation, and deep learning. Successful implementation of these ideas would be a significant improvement over the current state of the field and would overcome many of the longstanding challenges with poor image quality in a single image formation step. Let's consider this deliverable within the context of a biopsy, where the goal is to extract a small piece of tissue through a needle. It is often helpful to visualize the needle tip in the ultrasound image to ensure that the correct region of tissue will be extracted for later examination under a microscope. However, some patients produce worse images than others, as you can see here. And ideally, we would want to know with confidence at all times and for all patients exactly where the needle tip or the biopsy target is located, and then offer some sort of real-time feedback, such as what you see here for the needle tip location. And we can do this by inserting an optical fiber into the hollow core of the biopsy needle and implementing photoacoustic imaging, which can be thought of as ultrasound imaging with a laser. We can then use fiber optics to transmit laser light toward the needle tip, which is our photoacoustic target that absorbs the light, undergoes thermal expansion, and generates a sound wave that we can detect with a conventional ultrasound transducer. Photoacoustic and ultrasound images can then be interleaved to improve the biopsy experience. We can also relieve the operator from manually searching for the photoacoustic signal within the larger ultrasound image by attaching a robot arm to the ultrasound probe. And we call this entire system our photoacoustic-based visual servoing system, and we tested it in a controlled experimental environment to visual servo a needle tip, which houses an optical fiber and is rigidly attached to a translation stage that you see here, and is used to advance the needle into this ex vivo tissue, while a robot-held ultrasound probe is commanded to stay centered on the needle tip. Then we can overtake the robot, search for our biopsy target if we're located nowhere near it, find the target and then release, and then it's the robot's job to find the needle tip again as we guide the needle tip to the biopsy target. Here are some example photoacoustic images shown on the right with a segmentation of the images shown on the left and the green line representing the image center. And you see the photoacoustic signal from the needle tip has artifacts to the left and right and below the needle tip, which should otherwise appear as a point source in the image. And so this allows us to appreciate three possible automation tasks for performing a combination of ultrasound and photoacoustic guided biopsies. The first task is automated needle tip detection with no confusion from the artifacts that you saw in the example images. For this task, we categorize the needle tip signal as a point source and we detect it with photoacoustic imaging. The second task is fully automated ultrasound biopsy detection, which would mean that we would no longer have to overtake the robot to manually find our biopsy target if we're located nowhere near it. And we simplify our biopsy detection problem into that of a single cyst surrounded by tissue for the purposes of initial feasibility demonstration. The third task is to improve the visibility of both the needle tip and the biopsy target with an alternative path of advanced beamforming methods based on the coherence information. In particular, we want to improve the speed with which we can deliver these and other advanced beamforming techniques. So for the remainder of this talk, I will show you how deep learning can be used to implement these three specific tasks for image-guided biopsies. I'll discuss network architectures within the context of these three tasks, and then I'll end with a summary and outlook. To understand the potential of deep learning with regard to point source detection, let's start by visualizing a wavefront propagating spherically outward from a point source, which as a reminder is representative of our needle tip. We can then sense the recorded, or we can record the wavefront with our ultrasound transducer and get channel data that looks like this. Our goal with the beamforming process is then to create an image that looks something like the source that created the recording. But when we apply today's beamformers, we instead get something like this, where the shape that we would want to detect is distorted and the source appears at an incorrect depth, and we have artifacts to the left and right of the source. One reason we see these deviations from what we expect is because of fundamental flaws in the mathematical models that are used to create these traditional beamformed images. For example, we assume that there's a constant speed of sound when in reality, speed of sound can vary among tissue and among different patients. Another assumption that we make that's not true is that there's a single pathway from the source to the receiver. But in reality, there could be reflectors such as bone that would reflect the traveling sound wave. And here is a perfect example showing what would happen when we have one source that could be representative of our needle tip and a reflector that could be representative of something that has a different acoustic impedance such as bone. So when our source when the wavefront from the source propagates outward spherically and then encounters that reflector, notice how a second wavefront is produced. And when we record the channel data, we get the image that you see on the left. And then when we beamform the signals in the red box, we get the image that you see on the right. And we can appreciate the impact of these reflection artifacts when there is a single point source for the photoacoustic imaging case. But the same thing happens in ultrasound imaging, with the caveat being that the wavefronts that are sensed by the same ultrasound transducer are typically more complicated. However, the same principles hold in that the underlying signals look significantly different in the presence of reflection artifacts. So we can think of artifacts as the mapping of signal sources to the wrong location. And our goal with our deep learning approach is to map signal sources to the correct location. And we do this by inputting channel data into a network that has three outputs. The first is a classifier of the detected wavefront as a source or an artifact. The second is a confidence score associated with that classification. And the third is a bounding box, as you see in the example movie shown at the bottom of this slide. And this bounding box tells us the location of the true source. And we know this is a true source because we use simulations, much like the simulations that you saw on the previous slide, in order to train our convolutional neural network to detect the wavefronts. And we are basing our detection on the principle that wavefronts that are closer to our receiver will have a different wavefront shape than sources that are farther away. And this is because as the wave propagates outward spherically, there will be more time for the geometry of the curvature to expand for the sources that are located farther away from the receiver. And so what we believe we are learning is the unique shape to depth relationship associated with photoacoustic sources, because each depth will have a unique wavefront shape. And then we can differentiate this unique shape from a wavefront associated with an artifact, because the artifact will have an incorrect wavefront shape at any given depth. So after training with this in mind and testing with simulated data, the ultimate test of any of these networks is how well they perform on real experimental data, which we obtain by inserting an optical fiber into the hollow core of a cardiac catheter. And then that catheter was inserted into an in vivo vein. You can't see the vein or the catheter in this very noisy and poor quality ultrasound image, which suffers from attenuation at depth, but you can see multiple wavefronts in the corresponding photoacoustic channel data. We passed this photoacoustic channel data through our well-trained network that was trained from simulations and formatted the three outputs to produce a clearer indication of where the catheter tip is located. We can also display the output by itself, which is what we call our CNN-based image. And then we can compare the CNN result to the poor quality resolution results achieved with more traditional beamforming and immediately appreciate the benefits of the deep learning approach. To provide more details about how this network was trained, We varied multiple parameters during the training process, one of them being the amount of noise that exists corrupting our raw channel data. So we start with this noiseless case, which you see in the bottom left, and then we add increasing levels of channel noise up to -21 dB channel SNR. And then the graph that you see at the top shows our source and artifact classification accuracy in shades of blue as a function of the noise level, which is listed on the x-axis. We see that we have perfect classification accuracy in the noiseless case and in the -3 dB SNR case, and then accuracy starts to degrade as noise increases. However, what is remarkable about this result is that we have greater than 82% classification accuracy at the -15 dB channel SNR case. But when you and I look at the images created with this noise level, it is difficult for us to identify in the channel data where the sources or artifacts are located. So it's remarkable that the network was able to detect anything at all. And then as the noise level increases, the classification accuracy plummets, and there are more missed sources and missed artifacts, which are shown in shades of yellow. The associated ROC curves show the same trend for sources on the top and artifacts on the bottom. We achieve perfect classification accuracy for the noiseless case, and then the classification performance starts to degrade as the ROC curves transition farther away from the ideal curve as noise increases. Another parameter that we can vary is the location of our sources in our simulation when training the networks. And then we can take the wavefront location identified by the bounding box after testing the networks, which again, that bounding box is one of our 3 outputs, and we can compare the bounding box location to the ground truth source location from our simulations. And we can use this comparison to compute a location error, which is shown on the y-axis of these 2 plots for the axial and lateral image dimensions. The x-axis on this plot shows the same noise levels from the previous slide, and we see that our spread is fairly consistent, and so is our mean absolute error. We get mean absolute errors on the order of 0.1 to 0.2 millimeters. And this result is remarkable because it shows us that we have sub-millimeter error that is within the resolution of our imaging system. So this means that it's within the bounds, our location error is within the bounds of the physical limit of how well we can localize a target. And we'll see why this is important later. And for now, I want you to also be aware that there were other parameters that were varied, such as the number of sources and artifacts that we included during training, the speed of sound of the medium, and we even varied the type of receiver models that we use when receiving this photoacoustic signals. And then after having a well-trained network, we were ready to test it on experimental data. And we first tested it on this controlled experimental environment where we have 4 point-like sources imaged by an ultrasound transducer. And we can selectively illuminate how much of these sources would show up in the image based on the photoacoustic effect. And so in the photograph at the bottom center, we see that there are 2 of these sources being illuminated. And in the received channel data from this experiment, we have 3 sources illuminated. But when we zoom in on this channel data results, although 3 sources were illuminated, we know that 3 sources were illuminated because we selectively illuminated them. Notice that there are 4 wavefronts in the image. And then when we apply the traditional mathematical models to create a beamformed image, it looks as if there are 4 sources in our beamformed image. And this could be very confusing for a robot that may be relying on this image to find the sources and determine how to make its next move. And so we want to remedy this by returning to the raw channel data that created this image and passing it through our neural network to create our CNN-based image. And this CNN-based image has no artifacts because we do not choose anything that the network identifies as an artifact. We only choose to display the wavefronts or signals associated with the wavefronts that the network identifies as a source. This image also has high contrast because we set the amplitude with which we display anything that the network identifies as a source. And we have high resolution, even at larger depths, because the size with which we display the sources is related to that location error that you saw on the previous slide. And this location error, you saw it persists at a constant level across multiple noise levels, but it also persists at a constant level for multiple depths. And so this is what allows us to have high resolution at depth. And this is important for that in vivo example that I showed earlier, where we are viewing photoacoustic images obtained with an optical fiber inserted into a cardiac catheter. We see the traditional beamformed image again, side by side with the channel data and side by side with the CNN-based output. And although, you can see very clearly again why we would appreciate the benefits of the CNN output, we can possibly overlay the CNN output on the traditional images and maybe learn something about what the traditional images were trying to tell us where this catheter tip was located. And although this result was obtained with a cardiac catheter, it provides evidence that the method that we are presenting here will produce same benefits for needle tip detection, which was the first task that I presented for this autonomous biopsy detection system. Moving on to the second task of biopsy target detection, we train with simulations that mimic the physics of wave propagation, similar to the point source simulations that you saw earlier, with the one caveat being again that ultrasound wave propagation is more complicated. Nonetheless, we modeled a single cyst surrounded by tissue, and we have one plane wave transmission and a single insonification angle, because this is the most rapid method to acquire ultrasound data today. So if we're going to get this method to work and help us to improve speed, then it would be very promising if it works on this transmission pulse sequence. We varied multiple simulation parameters as listed on the left and shown in the diagram on the right, with the values and increment sizes now appearing. And then we created a simulated test set that contains examples that were not included during the training process. We then applied a range of different networks and training methods in order to produce our desired results. Highlights include first starting with one encoder and one decoder to build a fully convolutional neural network. And then we added hypoechoic cysts to our training data. We later updated our network to a generative adversarial network to create images and segmentations simultaneously. And I'll explain the rationale for this design choice in a few slides from now. We then updated our network further by removing the discriminator part of the GAN and including clutter masks in our training data. And this change was also complemented by switching the input data type from raw RF data, or raw radio frequency data, to raw IQ data, which is in-phase quadrature data. And I'll discuss the reason for this design choice as well. And then the final two networks included modeling the effects of attenuation during the training process and testing with subaperture beamform data, and finally adding more features during training to further improve the quality of our results. More details about any of these architectures are available in the 6 publications summarized on this slide. And now I'll go into the rationale for some of the design choices that I mentioned. So starting with simulated test data, we input this known ground truth into our ultrasound simulator, which produces simulated raw channel data. We then beamform the simulated raw channel data using mathematical models to get an image of the cyst. And you see here that this result has a lot of clutter. It has poor resolution and speckle that all work together to degrade detectability for an autonomous ultrasound biopsy system. The goal of our deep learning approach is to bypass the traditional beamforming process and instead create what we call our CNN-based image for ultrasound that emphasizes structures of interest, in this case the cyst, and de-emphasizes the structures that we do not care about for automation of the biopsy detection task. And in this case, the structures we don't care about is that background speckle. The dissimilarity coefficient between the ground truth and our CNN-based image in this case is 0.98, where 1 is the best that we can achieve. We plotted the measured dissimilarity coefficient as a function of the input cyst radius, and notice that the network performance degrades in the presence of small cysts. After grouping the results in integer multiples of cyst radius, we reported a mean and standard deviation shown in blue. For comparison, to experimental phantom results shown in green, leading to 2 insights. First, we confirmed that we can achieve good agreement between simulation and experimental phantom results, as you see here, because the green result matches the blue result very well. Second, we see that it is not possible for the experimental phantom result to be any better than the simulation test results. So this led us to question, what can we do to improve the small cyst errors that we see? And this is what led to our generative adversarial network, where we said, what if we can use feature sharing to force our network output to only produce a segmentation result if it can also only produce an image that actually looks like the beamformed image? And in doing this, we took a step back and we realized that we can have 2 outputs from a single input. And so we newly combined both image formation and image segmentation in a single step. And with this new goal, we said to ourselves, well, why would we want to reproduce the poor quality ultrasound image if we have this opportunity to produce an image that's even better than the beamformed result? And so this is what led us to update our network further. And capitalizing on this novelty, we first removed the discriminator because it was more complicated to train our network with this adversarial network attached to it. And not only that, but the presence of the discriminator did not significantly improve our results than the same network that was trained without a discriminator. And so we did this one change, and then we also changed our input data from raw RF data to raw IQ data. And we made this change because it allowed us to downsample more vigorously and pass more data through our network in order to create images with a larger field of view. And these changes produced 4 benefits in one. Not only can we have image formation and image segmentation in a single step, but we can also have clutter reduction, which was obtained by masking out the regions of clutter during the training process. And so this was our approach to achieve images that are better than the beamformed image result, which you can see by comparing the DNN image to the beamformed image to the left. And you can appreciate the clutter reduction by noticing how the cysts are filled with acoustic clutter in the beamformed image, and then that clutter is reduced because the cysts appear completely black in the DNN image. And that's because that's exactly what our clutter masks are masking out during the training process in order to create this DNN image that has reduced clutter. We also have a spatial compounding effect because we can smooth out the tissue texture with this network output. So all of these benefits are great for automated biopsy detection, but similar to the photoacoustic result, the ultimate test of these networks is to determine how well they perform on in vivo data. And so now you're seeing a result from an in vivo data, but you're also seeing more details of the final network architecture that I discussed, which was described on the previous slide and is described in even more detail in the publication at the bottom of this slide. We have 1 encoder and 2 decoders, and the 2 decoders produce 2 network outputs that you see, which have the same 4 benefits discussed on the previous slide. The first is a more interpretable DNN image of this breast cyst. The second is a simultaneous DNN segmentation output. The third is a clutter-reduced image in comparison to the beamformed ground truth image that you see on the right. And the fourth is that same speckle smoothing effect that I talked about earlier. In the bottom row, the DNN segmentation output is shown on the left, and it's also shown on the right in red, overlaid on the true segmentation. When we compare the DNN segmentation to the ground truth images, we see very good agreement, even for this small cyst with a radius of 2.3 millimeters. And so we achieved our goal of improving small cyst segmentation. And in the process, we got all of these other beautiful benefits that show the potential of getting simultaneous outputs from one single input of raw channel data. When we expand our field of view for the same network, which is now called CystNet1 on this slide, we see that we have false positives both in the B mode image produced by the DNN and in the segmentation result, as indicated by these arrows that you see. But when we include more features like lines and point targets to train a new network called SysNet2, which is actually the same network, just has more of these features that appear in the images included during training, we see that we're able to reduce the false positives that I'm pointing to with these arrows. We also see that this result is different from the results shown on the previous slide, and that's because we used focused transmissions as the input to our network to preserve the speckle texture. And to get these focused transmissions, we input subaperture beamform data. So we're not focusing the entire set, just a subset of the raw data is beamformed. And we input that into the same network architecture described on the previous slide. And we took this step because we recognize that speckle preservation is important for some tasks. And we show that our network architecture is versatile to deliver both speckle and speckle reduced images depending on the input data type, with only one single change to the input layer to accept focused data if we need it. And there are no other changes to the network architecture or the training process otherwise. So overall, this is very great for and exciting for an autonomous biopsy system. If we want to emphasize the structures of interest, such as the cyst, and de-emphasize the speckle texture. And it's also great for showing that once we build these networks, if we get someone or some other application that requires us to preserve the structure that we initially discarded, we can recover that information just with a simple change to the input layer. Now I want to switch gears and talk about how deep learning can improve the speed of computationally intense advanced beamformers. And this is the third task for automation of the biopsy procedure. This task is motivated by the short lag spatial coherence beamformer, or the Slsc Beamformer, which is the beamformer that I created as a graduate student. To implement this beamformer, we would take the same raw channel data that I've been talking about throughout this presentation, window it in time, or first, apply time delays to account for time of arrival differences. And then we window that delayed data in time, cross-correlate in space, and create the coherence function that you see here. And then we integrate this coherence function over the short lag region in order to create 1 pixel in the Slsc image. We can then repeat for multiple depths through our channel data, so in the axial dimension, and also for multiple lateral locations. And I contrast this with the end-to-end deep learning approach that I discussed in the previous section. Whereas you remember, we input raw channel data to a neural network and we output images directly from the input raw channel data. We can see from this contrast that the correlation step required for Slsc beamforming is one of the differentiators that is the most time-consuming between these two approaches. So now I want to introduce a third approach to replace the correlation calculation step with a deep neural network to potentially increase the speed with which we can deliver the Slsc beamformer. So we demonstrated this potential using our newly developed Cohernet architecture, which contains a series of fully connected layers. And this network accepts the raw channel data. And we now create 2 paths to, we now have 2 optional paths for creating the Slsc image. The first is shown at the top, which is the original approach that I mentioned on the previous slide, and it creates these original Slsc images. And this network was trained on breast masses. And so you're seeing several examples of the test cases that were not included during training, but it's still also breast masses. Our second approach is that we can take the alternative path that uses the Cohernet architecture, use that architecture to create coherence functions, and then follow the same process that I discussed previously, where we would sum up to a specific short lag value, and then get what we call the DNN Slsc image. And we see very good agreement between the original and the DNN Slsc approach. And the mean image to image correlation is 0.93 for all of these breast mass test cases. The network also achieves our ultimate goal of processing images at a faster speed, in particular 3.4 times faster than the original algorithm that contains many coherence calculations. Notably, the DNN approach also has greater fidelity to the original algorithm when compared to shortcuts that can be taken to implement this algorithm on a GPU. So this slide shows you the Cohernet architecture in more detail. The network was modeled using fully connected layers to model the convolution process or the correlation process. The input is one kernel of channel data and the output is the coherence function, R hat. And the network has an input layer followed by 4 fully connected layers and an average pooling layer. So we retain the 7-pixel size of the axial kernel until the end where we average it out through the average pooling process. And then we use the ReLU activation functions throughout until the final layer where we use a hyperbolic tangent to limit the network output between -1 and 1, similar to the mathematical cross-correlation function. And so for training this network, we implemented a custom loss function based on the mean square error, where the loss function includes a Gaussian weighting term W, which allows us to place more weight on errors in the short lag region. And we did this because this is the critical region for creating SLSC images. And therefore, it's the region that will most affect the SLSC image quality. And then these were the hyperparameters that we used during training. And here you see the individual coherence functions output by the network in light blue, and coherence functions calculated to make the original SLSC image are shown in dark blue. We see that the match is very similar between these two outputs, but in the short lag region, you see that we have the best performance. And that short lag region was modeled to exist up until about a lag of 25 and below. And we get this better match in the short lag region because we used that modified mean squared error loss function, which looks something like the plot shown up here. And we're placing more emphasis on errors in the short lag region with our Gaussian weighting function that you see at the bottom. And so Cohernet was trained and tested with data from in vivo breast masses, including cysts. And these are the type of masses that we actually want to biopsy for breast patients. And in addition to the in vivo breast mass data that we included for both training and a separate test set that was not included during training, we also wanted to ensure that our network was generalizable across multiple ultrasound data types and across multiple ultrasound system equipment components and configurations. And so therefore we created a data set with multiple types of test cases for us to test generalizability, such as phantom data collected with 2 different ultrasound systems, multiple ultrasound probe geometries, such as a linear array, a phased array, and a curvilinear array. And also we tested on a completely different type of in vivo data. We tested it on in vivo liver data acquired with an Alpinion system, an Alpinion ultrasound system. And here are the results of the curated test set to ensure generalizability of Cohernet using data that was not included during the training process. So we have 3 different transducer geometries, linear array, data acquired with a linear array, data acquired with a curvilinear array, and data acquired with a phased array. We have 2 different ultrasound systems, data acquired on the Alpinion ultrasound system, and data acquired on a Verisonic system. We have data from 3 different targets that are completely different from the breast data that was used for training. One is this phantom model. The other is a small parts phantom, a different kind of phantom. And the third is this in vivo liver data. Over this entire test set, we saw a mean correlation of 0.96 between the original SLSC images, which are shown on the left of each of these pairs, and the DNN images, which are shown on the right. And so you can appreciate both qualitatively and quantitatively that we are able to get similar matches even on this test set that is nothing like the original test set or the original training set. And these results are very exciting because they show that we can improve the calculation of the coherence functions to improve the speed of delivering advanced coherence-based beamformers. And they also show that we can learn physics-based features from raw channel data with good similarity to the ground truth and with a high degree of generalizability across many different ultrasound systems and data types. So in summary, we can appreciate that both ultrasound and photoacoustic images can be presented in this novel format that extracts information directly from raw channel data with deep learning. And the novel format is very much tied to the specific task being tackled. This allows us to have a one-step approach to address multiple historical challenges with image quality in a single image formation step with the assistance of deep learning. And this is possible by stacking multiple networks in parallel to produce multiple outputs from a single input. And our initial results highlight the vast capabilities of deep learning for image formation and for speeding up the delivery of images with more advanced beamforming methods, such as the coherence-based Slsc Beamformer. These results are ultimately very promising for autonomous robotic tracking tasks, which I use to motivate the problem. But as you also saw, these tasks can be expanded to include a range of other important challenges that we face and that we use ultrasound imaging technology for. These achievements motivated the formation of a challenge for our entire community, the challenge on ultrasound beamforming with deep learning. And one of the outputs of this challenge is curated data sets, code, and additional resources that are available for anyone who wants to tackle these problems. And I invite you to visit cubdil.jxu.edu to learn more about the vast array of resources that came as a result of this challenge. And if anyone is interested in trying those photoacoustic examples that were used to show how we can detect point sources, that is also publicly available at this GitHub site listed here. And so if we return to what I call a roadmap of some of the major advances in ultrasound imaging, my outlook is that deep learning is now starting to be the next frontier. At this frontier, many of the known challenges with deep learning still persist. For example, we still need training sets that include multiple patient variations in order for these networks to work. The networks need to be generalizable across different systems and target types and target shapes as well. And ideally, we would also want to have a good understanding of how our network is interpreting the raw data in order for us to be in charge and in command of what possible failures the network could produce. You've also seen throughout this presentation several different evaluation metrics that I use, such as dissimilarity coefficient. I've also used image-to-image correlation and network speed as as different metrics for quantifying the performance of our deep learning approach. And this shows us that the evaluation metrics can vary, but they must be tied to the specific imaging task. And this was also one of the beautiful outcomes of the challenge, because now we have an array of evaluation metrics and a bank of evaluation metrics that anyone can choose from if working in this area to help us as a field standardize what we're calling good performance and help us to compare different outputs using the same metrics. I've also shown you how we can address the grand challenge of achieving multiple outputs from a single input of raw channel data. And finally, I want to draw your attention to this recent special issue, which you can use to learn more about the different network architectures applied by many of my colleagues using machine learning in ultrasound imaging. And we have this guest editorial that we took great care to summarize the 17 articles submitted to this special issue, Deep Learning in Medical Ultrasound from Image Formation to Image Analysis. And so we have a great array of publications for anyone interested in this area to learn more. And I'll end by saying thanks to my dedicated team of students and collaborators who have helped to make all of this possible. Thanks also to my funding sources for supporting this work. You're welcome to visit my lab website for more details, pulselab.jxu.edu. Follow me on Twitter for real-time updates of our work. And thank you all for your attention. I'd be happy to take any questions.